about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hello, everyone, and welcome to day, I don't even know anymore, of Advent of Code. And with me is David. Hello.
Hello, I am excited to see what you've been working on. I have done a little bit of work as well. Let's get into it.
All right, let's get into it. So, the day before New Year's Eve, it was 10 p.m. and I was like, well, or 2 days before New Year's Eve. It was 10 p.m. and I was like, okay, I'm going to check on some of the Advent of Code problems, reread them, see if I have any ideas. And then just like that, it was 6 a.m. on the next day. And we have some new stars. And you have some new stars as well, because I remember that you said that there was a brute force approach, and then you also found a principled approach for the problem of finding a path through, the longest path through the maze. So yeah, let's get into it. I will kick things off. Here are the stars that I have. Not bad, huh?
Let's have a look. Oh, wait, I can't see your screen.
Oh,
so you have to share it.
One day I'll learn how to do this. Here are the stars. We even have some new effects here. And
oh, very nice.
And on your side, I think you have day 23, right?
What do I have? Yeah, let me compare. I think you have one more star than me. Is that right? Or two? So I am missing 1, 2, 3, 4, 5, and you're just missing 3, so you have 2 more than me.
Yeah.
Very
and
nice.
Not only that, but you have day 23, which I don't, and I have a day that you don't.
You have a couple days that I don't. Or no. Yeah, you have 2 days that I don't. 20 and 21.
Yeah. And I think 22 as well, right?
Oh, yeah, and 22, yeah.
That makes sense. All right. So, do you want to start by explaining your solution to day 23 and then I can grab that star? Or do you want to start by hearing me talk about days 20, 21, and 22?
Yeah, I'm more excited by 20, 21, and 22.
Okay. So, between these 3 days, do you have a preference? Day 20 is that machine that propagates pulses with flip-flops. Day 21 is that map that you will traverse in a number of steps and you need to find all the end locations. And day 22 is that stack of Jenga blocks and you have to disintegrate them.
Oh, wow. Yeah, I mean, I think I have the preference 21, 20, and 22. 21 I spent some time thinking about. And I came up with like a general idea, which is that so I have an Excalibur here. I wonder if this is the solution that you went with. I'll quickly share it with you. Share what I mean. Won't take a sec. So, if you can see,
I am here.
So if you go to the right where I am, there's this. So you see I've got... Oh. That's annoying.
Yeah. Nothing that a reload won't fix.
Hopefully. That's a good thing about web apps, is the state. Like, you can easily always clear the cache, generally. But it's taking some time. I don't know if that's...
Do you have a drawing that is complicated?
No, I'll just send you the image then. Check out this image.
Even the image is taking long to load.
Might be your internet then.
It might be. Let's see what OBS says. It had a red bar, but it is green now. Well, anyway, the modem is right there for what it's worth. So, what am I looking at?
So, you see where it's labeled 1, 2, 3, 4, 5, 6, 7, 8.
Mm-hmm.
That inner piece, that is basically our grid, which gets mirrored and replicated as we move in and out. And so my thinking is to count all the pieces 1, 2, 3, 4, 5, 6, 7, 8. And then you should be able, you can see like when you grow it to, I think it's 4 times the size. Or is it 3 times the size? It's double. I think it's double the area. Then you're able to count all of these pieces. And basically, I think there's some... That's when you get these like discrete amount of pieces. So the idea would be to like, you know, make some formula for counting those pieces as you get close to the number that they specify, and then manually count the final few if there's an offset or not. Do you see what I mean?
I see what you mean, and I guess let me show you my drawing. This is day 21, right?
Yes. This is day 21, yeah. So
here's my version of your drawing. We went for similar ideas.
The stream is frozen, sorry, on Skype.
Ah, so it really must be my internet. Let's turn the screen sharing off and on again. Here is my version of your drawing. And there are a couple more subtleties to the problem. So this is where we start. And
did you do it with SVG?
I did it with Excalibur and exported to an SVG.
Oh, okay, cool.
So the idea is we start in the middle, and the circled cells are the places that we can get to in an odd number of steps, because our goal is to find all the places we can get to with these many steps, and that's an odd number.
Okay.
And if you can reach this, for instance, in 1 step, you can also reach this in 3 by going back and forth, or 5 by going back and forth twice, or in that huge number by going back and forth a huge number of times. divided by 2. Anyway,
Yeah.
so because of the inputs that we got, the very carefully constructed inputs that have a huge line of dots in a cross starting at the start position. You can see that there are all dots to the left, to the right, to the top, to the bottom. And because there is this area here that does not contain any hashes, this losange that doesn't contain any hashes. And because this number of steps is an exact multiple, where is the number of steps? This number of steps is an exact multiple of the grid size. And because the grid is a square, and probably other assumptions, you have this very carefully constructed input such that you can play the trick that I'm about to explain. First, you do breadth first search to find all the places you can get to, and that takes in account all the walls. Also, the carefully constructed input has some edge cases that you will not find in the examples, and that is there are some places where there are dots that you cannot reach. For instance, here you will see that these dots in the middle are unreachable. So you have to take that in account as well. Do a breadth first search from the start. Don't simply say I will count dots and consider them even or odd or something like that. I have made that mistake.
Okay. Yeah.
And when you're counting the dots, put them in 3 different buckets. To explain what the buckets are about, you have to take note that when you see a repeat of the board, because now we have an infinite grid and the board repeats, when you see a repeat of the board, it will not have the same ending positions as what you have seen, because there is an odd number of cells in this board. The board is 131 by 131. In this case, I drew 5 by 5, but it's an odd number of cells. So when you reach the next copy of the board, the little dots here, the reachable cells, will be in different places. So I am calling these the even boards and the odd boards. The even boards are in green, the odd boards are in blue. And I call this an even board because you take an even number of board steps to get here. And when I say board steps, I mean like full boards. So you are 0 boards away from the origin. Here you are 1 full grid away from the origin. And here you are 2 full grids away from the board. So kind of the pattern that we do on a board level to find the ending positions kind of repeats itself over in this board of boards situation that I'm describing.
But why this even odd thing? Is it because it's an even number of rows and columns?
Well, think about it this way. If you are here in the beginning, and this is a map without any obstacles, no walls, and then you go up, and that's an odd number of steps. You can reach there. Then you go up again. That's an even number of steps. You will not be able to reach that in an odd number of steps. No matter what path you take, when you end up here, you are with an even number of steps, so that's not part of our answer. But then you take another step north, and this time you're going to circle this grid cell.
Yeah.
But now look down. This grid cell was not marked here in the original board. In fact, the boards alternate. So looking back here into the full input, if it was the case that this dot would be reachable in a board, on the next one up, it is unreachable, but the neighbors are reachable. And the next one up, it alternates again.
That makes sense.
Okay. So you're going to count in your breadth first search, you're going to count the reachable spots, and you're going to put them in 3 buckets. Bucket number 1 is the reachable spots in an odd number of steps inside this little diamond that is the frontier of our search when we get to the very outer edges. And in our example, like I said, we had a grid of 131 by 131. So we are talking about a diamond that is 131 on this axis and 131 on this axis, or in other words, 65 steps away from the origin.
Yeah.
Okay, so you put these dots in the even bucket. And now let's also say that this is inside the diamond, or the inner diamond, as I will call them in the future diagrams today. I will show you. So this inner diamond goes into one bucket. While you're doing that, the map is the same, the obstacles are the same. So if you find anything that is reachable in an even number of steps, put that in the odd map. Like so. So these two are complementary. Every time that you step on a cell, it's a dot. In other words, it's reachable. You're either putting them in this bucket or in that bucket.
That makes sense.
So far, so good. And the third bucket is everything that is outside this diamond, the outer diamond, as I'm calling it. So this region on the upper left, the region on the upper right, and it doesn't really matter the parity. It doesn't matter if it's the even board or an odd board. They all go in the same bucket.
Oh, okay.
Okay, so now let's take this counting that we did, and we only traversed this board once, okay? So you will visit, with a breadth first search, every possible dot in this map, only once.
Yeah.
And you will put the counts in the right buckets, and you will end up with three numbers. The numbers are the number of reachable dots in the even map inside the diamond, number of reachable dots in an odd map inside the diamond, number of reachable dots outside the diamond, the outer diamond. Okay?
Yeah, that's a bit confusing to me that you have this, you put them in the same bucket regardless on the outside.
It's true that originally I put them in separate buckets, but as I will show you, you will see the two buckets always together. And here is the part that took me hours and hours and hours to figure out. This drawing, it's mostly Command-C, Command-V, so it's not too complicated, but it took me probably like 4 or 5 hours to come up with it, because it's a similar problem. Remember the day that we used Green's theorem to find the area of a figure, and we had to make sure that we would count everything, but we didn't want to double count? It's the same story.
Yeah.
We have to find a way to cut this pie so that you don't overcount and you don't undercount. And there are different ways of doing this, and here is my way, which, as far as I could ascertain on Reddit, has not really been done exactly like this by anyone else. So, the inner diamonds are here in orange, and they are inner diamonds for each board separately. And we are going to look at these regions in red, which would have been the answers if we had a single board, or if we had a grid of 3 by 3 boards, and if we had a grid of 5 by 5 boards, and if we had a grid of 7 by 7 boards, and so on and so forth.
Yeah.
And in the final answer, we will have a huge number, which is essentially this number divided by 131. That will be the size of your real grid. Okay, so how do we go from this one, this inner one, to the next one? Well, the number of blue inner diamonds, the odd maps inner diamonds, grows up by 4. And that is, it goes from 0 to 4. And what if we take the next step, and never mind these parts that are still missing, I'm gonna get to them. Then how do you grow from a board of 3 by 3 to 5 by 5? Well, this time you will see no.
Sorry, say that again. How you go from a step of 1 to 3, was it? What was the step?
Yeah, so I'm going to explain this in 2 parts. First, we are going to look at the inner diamonds and then at the outer diamonds. The
Okay.
inner diamonds are these delimited in orange, and the
Yeah.
outer diamonds are everything else.
Yeah.
So starting here with 1 by 1, you'll see that on the next step, we will add blue boards, but no green boards, looking
Yeah.
only at the orange parts. Then from going from 3 by 3 to 5 by 5, you will only see addition of green boards,
Yeah.
but no blue boards. And then when you go from 5 by 5 to 7 by 7, you only see blue boards again, and no green boards.
Yeah.
So we see a pattern. We start by adding blue boards, and we alternate blue and green and so on.
Yes.
Now we need to...
And it's
Huh?
1, 4, 8, 16.
Yeah, so it goes from 0 to 4 in terms of blue boards. The green boards go from 1 to 1, 2, 3, 4, 5, 6, 7, 8. And then from 4 to 1, 2, 3, 4, 5, 6, 7, and so on. And then if you just count these things, you end up with these counts. And the inner diamonds go from 1 even diamond and 0 odd diamonds. That's this one right here. And then it grows to 4 odds and 1 even. And then it grows to 9 evens and 4 odds. And then 9 evens and 16 odds.
Were you doing this on your iPad?
I was using a drawing tablet, a Wacom.
Oh, okay. Yeah, it makes sense, because I was wondering why you would write it otherwise. But yeah, that makes sense. That's cool.
Yeah, so if you look at these numbers for long enough, you will find formulas that go from this into what you need to add. So I think it boils down to like this minus 1 times 2, something like that. And yeah, because 3 minus 1 is 2 and times 2 is 4, and that's what you add to the blue. And then 5 minus 1 is 4, times 2 is 8, and that's what you add to the green. And 7 minus 1 is 6, times 2 is 12, and that's what you add to the blue. So I think that's the formula. And then Bob's your uncle. That's what you do for the inner diamonds. For the outer diamonds, the argument is pretty similar. You just have to count them carefully. So you start in the middle. How many outer diamonds you see? Well, don't even think about it that way, because we don't see a full inner diamond. So let's just go to the next one. If you have a grid of 3 by 3, these inner diamonds are going to lock in a very nice way. So look at, for instance, 1, 2, 3, 4. Look at these 4 segments. We know by construction that they will always appear combined, and that they will make a full green inner outer diamond, right? Because this part complements this part, and then this part complements this one. So you get one full green outer diamond, and by a similar argument, you get a full blue outer diamond over there. And that's why we were able to put the outer diamonds for green and blue in the same bucket, because they will...
I really like your coloring system, by the way. It's very helpful.
So they will combine, and they will end up being counted only once. And my original implementation actually divided between green and blue, and then I realized, oh, they always appear combined, so I might as well just count them once anyway. And then how many outer diamonds you will have? Well, between these two occurrences, you will have one full outer diamond, counting green and blue. And then if you count this one, you'll see 2. So you say that for a 3 by 3 board, you see 2 evens and 2 odds.
Okay.
And then you rinse and repeat. So here you will see 1, 2, 3, and 4. And plus the 2 that you have already seen. So you see 4 new ones, and you have already seen 2, so that adds up to 6, and then 12, and so on. And then again, if you stare at these numbers for long enough, you will start to see a pattern, and I don't even remember what the pattern is. I think it's just -1, and then you add to the previous one. Yeah, because let's say that this was 0 plus 3 minus 1 is 2, 2 plus 5 minus 1. 5 minus 1 is 4, plus 2 is 6, 7 minus 1 is 6, plus 6 is 12, and so on. So you found a formula for this as well. And then you do that until you reach the board size, and you have counted everything only once and at most once. And
Brilliant.
I will show you what the code looks like, but it is nothing to write home about. It's very simple indeed. First is me doing parsing and finding the start position, which in this case is a copy paste from the previous part from 21.1. In fact, I could have hard coded this because this solution is very dependent on a specific shape of the inputs. Then I have my plots. That's the nomenclature used in the description of the problem, but those are the counts of spots.
Sorry, what was that first bit? Sorry, show me again.
That's me finding the starting point of the board.
Yeah.
Which is something that we have written for part 1 when you were doing it.
Yeah, sorry. Yeah.
And then I'm doing a breadth first search and visiting everything that I can see on the board and putting everything in 3 buckets: the even inner diamond, the odd inner diamond, and the outer diamond. And this is just going to count the number of places I can get to in a particular number of steps. And so there isn't a lot of surprises here. I'm using a work list. I'm pushing things into the work list. I guess perhaps the only neat thing that I'm doing is that instead of having a set of scene locations, I just mutate the map and I put a V there for visited.
Got it.
And then I don't visit the same place twice. Anyway, and this is the bulk of the code, really. This is where it gets interesting. This is the implementation of that whole idea I showed you, and it's not large. It's not a huge amount of code. So you start with 1 inner diamond for that green thing in the middle here.
Yeah.
And then you are going to grow the current map size from a map of 1 by 1 up to this number, which is that huge number there, divided by the map length and some off by 1 things that you have to take care of. You're going to be growing the size of this board 2 steps at a time. So from 1 by 1 to 3 by 3, 5 by 5, 7 by 7. And what was the question?
What's the off by ones going on there? And also, where's steps defined? Steps is the global steps?
Steps is that huge number from the problem statement.
Right.
And you have to multiply the number of steps by 2 because you're going to the left and the right.
Yeah.
And you have to add 1 because you have started in one place.
Okay, yeah.
So this is the number of little dots that you will be able to visit on this huge line here in the middle. The number of dots is this formula, and divide that by the length of the map, and you will get the number of maps that you will see overall.
So I guess this is just like, it's the same as the width of the
Yes.
board, that number.
Yes.
Okay. Cool.
So you're growing this map of maps 2 steps at a time, 1 by 1, 3 by 3, 5 by 5, 7 by 7. Then you're adding to the sum the number of inner diamonds that you will see, and these inner diamonds are these orange things, and I alternate from odd to even every time.
Yeah. Yeah.
And I do the formula that we saw before. So current map size minus 1 times 2. We saw that.
Yes.
And then the number of outer diamonds that you will see, which apparently has an even simpler formula. Oh yeah, because I added these 2 together. So if you add these 2 together, it becomes 4, and this becomes 12, and this becomes 24, and for some reason it works out. I'll not even get into that.
Yeah.
And then you print the sum in the end. and that's it. The code runs absolutely fast, of course. And
I'm sure. Well, congratulations. That's really beautiful. That was not an easy problem. That
it
was
was
tricky.
tricky. It was probably one of the trickiest that we have seen. And in the end, it's very satisfying that my argument here works. It's a counting argument that is perhaps a bit tricky,
Yeah.
but very evident once you spend enough time looking at it. And then I looked at how other people solved the problem, and it sort of amounts to the same. But what people did is that instead of doing this construction one by one, if you notice that you are summing some things over and over, you could find the formula that does multiplication instead of addition, if you know what I mean, instead of repeated addition. So instead of saying like 3 plus 3 plus 3 plus 3 4 times, you could just say 3 times 4. You know what I mean? You could compact this into a single formula that, given a size, it will output a sum. And then people have found that formula. And
Yeah. Could you use linear programming or something to work out the formula with enough? Like, you could just have like a set of equations, and then you just have to have some constants in there.
that's more or less what people did. Yeah, so they solved the problem, perhaps even using the brute force solution from part 1. It doesn't really matter. Solve the problem for 1 by 1, solve the problem for 3 by 3, solve the problem for 5 by 5, and then use some, and then it becomes like a cubic formula. And then you can find the coefficients for that formula, and that's the generalized formula.
Yes. Yeah. That's a really cool way of doing it too.
Yeah. Right. So I think that there isn't anything like, oh, this is just an application of such and such theorem. No, the way to do it was either by finding the pattern like I did, or finding a similar way of counting. People came up with all sorts of ways to slice this pie. Or you can do it in the finding the cubic formula idea, which kind of amounts to the same. It's a different way of, an algebraic way of finding the pattern instead of a geometric way, but it amounts to the same. It's just finding the pattern. And of course, everything is only possible because we have a very carefully constructed input. And lots of assumptions in place.
Yeah, that's what I was going to say. It's like incredibly handcrafted, this problem. It's like so specific. I mean, probably that does have some other problems which it could be applicable to. It's like inspired from other things, but it feels like a really distinct puzzle.
Yeah. And I really liked it. It was very satisfying, even though it took me a long time. It was very satisfying because all this time I was just working on the drawings and I was thinking of how to do this. And then when I finally got to the implementation, I was like, okay, I'm going to implement this for this map. I'm going to implement this for this map. I think I even have it still. Yeah, here is that map with no walls. And then I implemented this map and I saw that my countings were right. The inner even was 4, the inner odd was 9, and the outer was whatever it is. And I was like, okay, this is correct. And then I implemented this for 1 by 1, 3 by 3, and I was like, okay, this is correct. And I got these numbers. And then I finally ran it for the big input, and I had the right answer. So it was like thinking for hours, programming for 10 minutes, and finishing it.
Beautiful. Wonderful. Brilliant. Let's see day 20. Let's see day 20. Because that one, I really actually didn't know where to go.
Right. So for this day, you unlocked the puzzle, in fact, because I implemented your idea and it worked out. Remember that we drew, I think I even have a drawing that I also produced for my own inputs, and I wrote the GraphVis thing. So we looked at this, and we saw, there are 4 distinct subgraphs here. So
Yeah.
it stands to reason that they can be solved independently, and then we can LCM the cycles. That's
Yeah.
exactly what I did, and it works.
Okay.
As simple as that.
Brilliant.
So just do, this is day 21. Do the simulation like we did. And once you, I also marked these guys that contribute to the answer. I marked them in my code. So if I ever see one of them being flipped, then I count the number of steps and I do the LCM, and then I print the LCM. So most of this code you recognize as code that we have written together, because it's doing the logic for the flip-flop and the logic for the broadcaster, pushing into the work list, all of that. So the only real modification is that I have collected where did I do this? Here. I have collected the sources that contribute to Rx. So I jump from Rx to NC, and then I look, what are all the nodes that are connected here? And then if I see that I received a pulse in one of those nodes, then I remove it from my work list and I push, I LCM that, and that's that.
But what is in the code? So NC is not included in that list?
Correct. It's not. It doesn't have to be, because NC is just a conjunction node to gather the inputs. Yeah. It could as well have been Rx that was the conjunction node.
So you just keep running. You keep running it until one of them lights up with a low pulse.
Yeah, I think it needs to be a high pulse, but yeah, I just.
So if the pulse is high and it is the node that we're interested in,
one of these 4,
then yeah, what are you counting? What is the LCM?
I am LCMing the number of presses, button presses that I have seen so far.
That's so smart.
Because that's the question, right? How many button presses are necessary?
Yeah, that's it.
So in a way,
you're right.
This is a different lick of paint on the same problem that we have seen. I think it was like day 8 or something, very early on.
Yeah.
And I would say that this is even clearer that you can LCM, because there aren't those like tails in the beginning that threw me off.
Yeah.
Yeah, and another way of seeing this is that each of these is a binary counter, because you can see like a trail, and this is something that you have noticed as well, and people on Reddit also have beautiful drawings of this. It's a binary counter, and when you see these arrows poking in from other places or poking out and going to other places, that's how you tap into the digits. So this is going to be like your first digit all the way to the right. This is going to be your second digit, third digit, and so on. And I don't really know where the arrows point, but let's say that if you're interested in bit number 5 being on, then you put an arrow from it back to the beginning, or vice versa. And that's how you can say, this is going to be counting up to 155 or whatever number you want. And that's another way of solving the puzzle. Instead of doing the simulation, you can look at the structure of the graph, because again, it has been very carefully constructed to be a binary counter. And you can use graph algorithms to determine what these numbers are and then LCM them. Instead of simulating, you can just look at the structure of the graph.
Yeah, I was going down that route, but I couldn't work out exactly what they do when you point into somewhere down the subtree or up the subtree. You say it sort of selects that bit. Is that what it does?
That's more or less my intuition, but I haven't really understood the details of how the arrows work out. I was happy to learn that they were binary counters, that the arrows represented how you tap into the digits. Stop there.
Yeah. Nice. Okay, cool. And then I guess finally day 23
Well, that's something that you show
or
me
day
because
22.
I have day 22.
Okay.
So
Yes, this one is a cool one. I can't remember what the problem, part two problem was. I didn't look at
So
this.
day 22 is a bunch of Jenga blocks, and they are falling, and then they're gonna stop. And then the question is, if I remove one of the Jenga blocks, how many of them are gonna fall? Okay, maybe 5. Okay, so put it back in. Now, if I remove this other one, how many blocks are gonna fall? Let's say 3. Okay, put it back in. And if I have removed this one, how many blocks would fall? 8. Okay, put that back in. And then add the answers. So in my example, 5 plus 3 plus 8.
Yeah.
And my solution for this was something that we have discussed together, and it is, again, very straightforward. Just do the compaction algorithm, the settlement algorithm that we have done together. And then look at, so you do it once for all the blocks. Do it once as a reference. Then literally remove one of the blocks from the list, run the settlement algorithm again, and compare. Is this block in the same position as it was in the reference or not? And do that for each and every block. Add the answers, Bob's your uncle. So brute forcing, essentially.
Sorry, explain that again. I missed that a little bit.
Of course.
So you run it.
Yeah. So there is a way for, there is like a subfunction that we are using that for any combination of blocks, it will settle the blocks, right? Okay.
Yeah.
So run that with all your input. Run that with all the lines. There are not that many, but run the algorithm once with all the lines. That's going to be your reference. That's where the blocks would fall if no blocks were removed. Great. Now, remove this block, run the algorithm again, and compare. Does this block fall in the same place? Does this block fall in the same place? Does this block fall in the same place? And so on and so forth. Okay, and then you count. Then remove this block, run the settle function again, and count. Does this block fall in the same place as the reference? Does this block fall in the same place as the reference? Add up your results, and that's that. It's essentially a brute force solution. I'm literally removing a block and settling all of them again.
Oh, okay. So, yeah. So you basically, it's the same solution. You didn't do anything to optimize it. It was just fast enough. Okay.
As it turns out, this is fast enough. There are not that many blocks, and the settling algorithm is pretty fast because I think it is linear. Yeah,
I think linear.
So probably the whole solution is quadratic or something, cubic, but whatever. It's a small enough number that it just works out. Now, if you wanted to be clever about this, you could do the settle once and do the thing that we did of detecting who is supported by whom, which blocks support what other blocks, and there is a graph algorithm that you can employ to find which nodes are dominated by other nodes. In other words, in graph lingo, domination is when you have to pass through a node to reach another node in a directed acyclic or a directed graph, maybe. It may even be cyclic. So if it is the case that to reach node B, you must pass through A, then it is the case that A is supporting B, and if you remove it, then B will fall. So if you can look at the graph that was created from the supporting system, and then you can look at you compute these algorithms for graph domination or whatever it's called, and it works out. But I didn't do it that way. I did the brute force way, and it was fast enough.
Cool. Very nice. Very nice indeed.
And
you got through. You got through a lot.
That was a long night. And then I have some ideas of how to do day 24, and we can either discuss that or you can show me the solution for day 23. But day 24 is complicated.
Yeah, so I sent you the solution to day 23, so you can just tap on the link. I sent it on WhatsApp, but I can send it here as well if you want. Oh no, my screen just went. So long did it? What was day 23?
Day 23 is you're taking a walk on the park, and the park is a maze, and you want to take the longest walk you can without repeating.
Yes. Yeah. I actually have some because I sent you an explanation on WhatsApp, and I have some doubts about my explanation, or at least I have some thoughts about it.
So if I remember correctly, you solved the problem not once but twice. First by brute forcing and leaving it running for a day and a half, and then again with a smart and fast algorithm, right?
Yeah, so the smart and fast algorithm it's interesting because it should run a lot faster. Because I don't know, I think there was, because I saw some people who tried to do it. Basically, my brute force was still with all the shortened nodes. So it still had all these, like, I just stored, rather than traversing everything, I just stored the distance between the things. And I saw some people solve it online, and they got that. They didn't, like, their brute force solution ran super quickly for that. So I don't know, maybe I wasn't running the same brute force. I'm sure I was. I'm kind of surprised that it took so long to resolve with that shortened version. However, the
I can feel the struggle, man.
version 5. Yeah, there you go.
So
yeah, because I did lots of different versions of the visualization and stuff. Yeah.
Okay, and this is the smart algorithm, not the brute force.
Yeah, so this second one, it just resorts it. Well, so there's the junction nodes, and then there's the really smart one is yours, where you actually sort by, you invert all of the distances, make them all negative, and then you can do Dijkstra, because now you can get the shortest path, and it just works.
I don't get that. I know that that's a thing because I looked it up, and I don't get it. So let's see if I can explain why it doesn't make sense to me, and then you can explain why it actually makes sense. The problem is, first of all, Dijkstra is not supposed to deal with negative weights. But never mind that. The second problem I have is what is the best way for me to explain this? Okay, I guess the best way for me to explain is to draw. So, and these are going to be the drawings for for day 24. But nice. My idea is, you are doing a search on a space, and you start here, and then you go up, and then you reach here, and then you have an option. You can either go right or you can go up. And now the weights are negative, so this is going to be like -1. And this is going to be -1 as well. And I'm not going to keep drawing the -1s because I don't have my tablet here, and it becomes annoying. But you know that this is going to have a weight of -1, and that's going to have a weight of -1. And then arbitrarily, the algorithm is going to decide to go up. But that's going to be wrong. I am telling you, the longest path is going to the right, but it's going to go up. And then when it goes up, the weight of this path is -2, and the weight of this path is -2, or the weight of this path is, we haven't explored it yet. But if you were to explore it, it would be like -1. Now, between -2 and -1, which is the shortest, the smallest number? It's -2, so you're just going to keep going here. And then there. And you're never going to explore this path. Eventually, you will find a path to the exit, which will be not the longest, but it will be a path, and you say, aha, I'm done. So it doesn't help with the problem. The real solution must lie in alternating, exploring this path, now exploring this one, now exploring this path, now exploring this one. Oh, I have found the end. Oh, but I'm not done. I could explore this path. Okay, so I'm going to keep exploring it. Do you see what I mean?
I 100% see what you mean. Yeah, the only way that it works is if when you add a node, it works against its priority.
Exactly. And to do that, what is the point of negating the numbers? You could just sort the list on the other direction, right? Always get, if you want to find the longest path, always sort by the shortest, but keep going until you can't go anymore. But that's a brute force search. It explores every possible path.
Yeah, I actually can't explain that. You make a very good point. I wonder if there was some caching issue, which meant that this ran. I thought it was running a different algorithm to the one that it did, and it completed very quickly, but it was actually running a different algorithm than the one I thought. Because now that you say that, yeah, it makes a lot of sense. That wouldn't improve things. It would just do the greedy situation. Each time you add it, it's going to be the shorter path. Unless I was like sorting it I was ranking it by the length or something. How was I doing it? Yeah, I was sorting it by the distance. So the shortest distance first.
Ah, but you don't stop when you find the destination. You keep going until you have exhausted the search space.
I'm actually adding the distance is the current distance minus the next distance.
Huh?
Weirdly, I think I might have some double negative magic which is going on here. If you actually look at the code.
Okay. Any particular line I should go to?
Line 408. See how I'm taking away the distance rather than adding it.
Mm-hmm.
But if it's a negative distance, then it will add that distance.
Oh, the distance is already a negative number?
Yeah. Oh no, maybe it's not. Maybe that makes sense.
And then you're sorting by... So you are sorting by A, B, A, B. So that is going to create an ascending.
Yeah.
Goes up. So you are getting the first element from an ascending list, which means you are exploring the shortest path.
Yeah.
And... Ah, but look at that. When you do find the end node, you don't break, you continue. That's the trick.
What do you mean? That I have to explore all the paths?
Yeah,
yeah.
You are exploring all the
It's
possible
still
ways of getting to the destination.
Yeah.
How come this is fast?
You know what? I think it is actually that the brute force was running. Now that I'm thinking about this and looking at this, I think simply just making junction nodes made this fast enough.
Because I saw that you were doing not just going step by step on the graph, but you are looking at the whole section before a decision and counting that as one node and this as one weight.
Yeah, it was the pre-processing. I think what happened is, this is the conclusion that I've come to, the junction nodes made it fast. this is what makes sense to me anyway. This is not actually what my findings were. But the junction nodes made it fast. And that my brute force, which I thought I was brute forcing the junction nodes, I was actually brute forcing the really slow iterative version rather than the junction nodes. And that the sorting and everything made no impact. That's my only conclusion. That's the thing which makes the most sense to me.
All right, that I'm happy with that. And how do I run this? Because I see that there is also some visualization stuff. So what do I need to do? I want to get my star.
You need to npm install Parcel. And then, I mean, do you need to install Parcel? Because this code could just run, actually. Yeah, I don't visualization stuff going on.
Well, there is code for this. I'm not sure it's called.
Does it call visualize? Yeah, does it call visualize path? Because there's one call to visualize path. So if you just comment that out, it should be fine. And then are there any imports? No. Okay. Well then, yeah, you can just run it with TSM or TSC or whatever. But you could also run it with Parcel.
Well, I stopped the Parcel installation.
Okay.
And this is going to be day 23, part 2. And do I have anything of interest in this day 23, part 2? No, I don't. So I may remove that. Add day 23, part 2, and this is going to be TypeScript this time. Paste it in, remove the visualization, then...
You could chuck it through like TypeScript online so that you get rid of the types.
Nah.
If you...
I already have TSM installed from previous days.
Okay.
Wait a second. These are my inputs?
I wasn't running it with your inputs, but maybe you already pasted it. I don't know.
Just in case. Okay.
It's because it's a new file, so you didn't see the diff.
Maybe. And I have to
Oh, you need
say
to do that.
require TSM. And now... Yeah, you're finding longest paths. And they are getting longer and longer.
Yeah, but it was a lot quicker than this.
You're saying that you ran this code and it was quicker on your machine than it is on mine?
Yeah, it's like seconds.
That's just rude. What is wrong with my machine?
Oh, there you go. Okay, that's fine. Yeah, that's probably acceptable.
Good job!
There we go.
So if we understand this code correctly, then...
Yeah, I might have to do some exploration to verify that it's correct. Because if you get rid of the sorting, it shouldn't get there. What I found is by getting rid of the sorting, it was a lot slower. So just get rid of that line 386, comment that out. I mean, it is going to find more paths, probably.
My theory is that no, because you don't break, you continue. So you are exploring every possible path. You are just exploring fewer paths because you did the smart thing about parsing the maze. And I think that the execution time will be the same. And I think that... and it may be even faster because sourcing a long list will be expensive. So this may be even faster, actually.
I meant more that you are going to be logging more paths. potentially.
Perhaps. Okay, so what we learned is that perhaps the whole thing about negative distances doesn't really help anything, right?
Well, let's wait until this completes to verify that.
Yeah.
But yeah, I think so. I think
And
just double check how distance is defined. If you go, because like, I mean, it must be positive distance, but
you're now talking about how we constructed this distance
yeah,
in parsing the graph.
yeah.
It must be related to this distance. And you're adding distances.
Yeah, so I think what I did is I got all the junction nodes, and then for each junction node, I put it through this for loop and said, okay, the distance is 0, and then like find out its distance to neighboring junction nodes.
But it seems like distances are positive here.
Yeah, distances are positive, yeah.
And
there you go. It is taking longer though, isn't it? Like
it
quite
is.
A lot like
maybe because you sort, you end up creating fewer states. The sort is sort of turning this into a depth first search, and then the depth first search may prune the state space faster.
But how could it prune the search space faster if it's doing brute first search anyway? Like, it's not pruning anything, it's just doing all the possible paths, isn't it?
Well, there is the pruning in the sense of revisiting a place you have been before.
But you still do that anyway. Like, there's no... You don't do that. There's no, like... it's only if there's, like, a loop within your own path, right? So if you look at... There's path.includes next. That's the only thing that we do to prune the search space. And that's only... The path is only within this particular... Maybe it's like constructing, somehow we skip line 397, and that's a really slow line, because we are, like, if we change that line to be like, check if it's in the current path or it's equal to the current position, rather than constructing a new array each time, there might be like some wasted effort for some reason. But to me, this is pretty slow. Like, quite a lot.
Definitely slower.
But why? Because your logic made a lot of sense as you just explained it then.
And where do you even... I suppose that these distances that we are subtracting, they are going to be a large negative number. Where do we even turn that into a positive number? Oh, here. We do it here. Okay.
Yeah.
Yeah, I'm stopping this and I am calling it a solved mystery.
It's always nice when you're able to create a scenario where it works and you don't know why.
But here we are. Only one day missing.
Yeah, because then day 25 will just autocomplete, won't it?
Yeah, exciting times. I have not finished day 24, but I have thought about it a lot.
Okay.
And I have already ruled out some false paths. To recap, what happens in day 24 is that we have hailstones going in each and every direction, and these are the initial positions of the hailstones and the initial velocity of the hailstones. Of course, there is no air resistance, no gravity, no acceleration, no nothing. Constant velocity. and they are just moving across the space. Then our job is to position ourselves in a perfect spot and throw a rock in the perfect velocity, in the perfect direction, such that the rock will hit every hailstone. And of course, when the rock hits the hailstone, it does not change direction, it does not lose acceleration, or doesn't lose velocity. There is no deceleration involved, nothing. And all the hailstones are weightless, have no mass, and the rock has no mass as well. So it's a matter of finding in this huge space where is your lucky shot, where do you need to be. And there are a couple constraints, like you have to be in an integer position on the grid, and you have to have an integer velocity as well. These numbers are not fractions and that sort of thing. So do you remember the problem?
Yes. So the first, I don't remember the difference between part 1 and part 2. You have these hailstones going. The first part is what was the question?
In part 1, they were sort of asking a stepping stone question. I guess there is a pun in what I just said. But part 1 is just forget about the z-axis and just look at the x and y axis and look at the velocities on the x and y axis. And forget about the fact that the hailstones are moving in space. Just trace lines all the way into the future. Do the lines cross?
Yeah.
And if they cross, then add to the solution, right? How many lines will cross? So for every possible pair of hailstones, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 3, and so on. For every possible pair, find where the lines possibly intersect.
Yeah.
If they do, count that as an intersection, add everything up, and make sure that the intersection doesn't happen in the past.
That's right. Yeah. I remember.
They were asking this as a way of practicing, like, do you really know how to find the intersections of two lines?
Yes.
Because that will come in handy for part 2, I think.
And then part 2 is 3 dimensions. And is it the same question to count the number of collisions?
No. Now we are asked something much more interesting. We have to be in a certain place and throw one rock. This rock has to hit every hailstone. So it's not simply a matter of this rock has to intersect with the paths of all the hailstones. No. It's not only a matter of intersecting. It has to be intersecting such that it will hit the hailstone at the right time. When the hailstone is passing through the intersection, the rock needs to be passing through the intersection.
Yeah. And we need to output the rock.
Yeah.
Which will...
Yeah, we need to know where the rock was in the initial position. And...
do we not need to tell them the velocity?
We don't need to tell them the velocity. I guess their point is, like, if you know the position, you figured out the solution, don't give us the velocity, we don't care. Just give us the coordinates of the initial position.
Yeah, okay, cool.
So, do you have an intuition of how you would go about this? Because I have some ideas, but I would love to hear yours as well.
I guess you would have to My initial thought is to see like where they are generally going to be close together.
There's one more thing that I should say about part 1 that may be a hint for part 2. You know that whole finding if the lines intersect? It was not simply looking at the lines and seeing if they were intersecting, but if the intersection was in a certain area of interest. which in the examples was a small area of interest, but in the real case, it was a huge area of interest. And also, all the coordinates are huge in the real inputs. Not the velocities. The velocities are reasonable. They are larger than the examples, but are reasonable. But all the coordinates are like way up there into outer space. So maybe there is something to do with this area of interest, like a binary search in the area of interest or something like that.
I mean, one idea, it's not a solution, is you could simulate all of these lines step by step, and then see when they start to converge. Like, see when they start to become closer and closer, where the distances are less and less. And then you could think about creating a line which would intersect that region. It's a very intuitive, like, real world. Basically, if I was throwing a stone, I'd see where they're all close to each other, and I'd throw it there. And that's my general thinking. But I don't know. What are you thinking?
Well, the tricky part for me with that is that the way you're explaining it, I am sort of imagining like I am in the field and I'm looking at the rocks, and you're sort of asking the question, when are all of them going to align, right?
Yeah.
Like a beautiful alignment of the planets. But that's not the point, because the rock takes some time to go from one hailstone to the next. So I don't want them all to align. I want them to all align over time on the path of the rock. So it's not the case that I will see the rocks in full alignment in front of me. It's the case that I will throw a rock, and as the rock is navigating through the space, it's hitting all the milestones, all the hailstones.
Yeah. I don't know. I might be tempted to just visualize stuff to see what it looks like, and then maybe I could get some intuition from that. I'm not sure. What did you think about doing?
Yeah. So I sort of went down this route of visualization, and my first thought...
Oh, really? It's cool.
Yeah, I didn't visualize everything in a two-dimensional space. I visualized this in a different way that I'm going to explain to you now. So my first insight was, we used in part 1 to do the intersection and all of that. We used the formula for a line in a Cartesian plane that was y equals to m times x plus c.
Yep.
And there is another way of conceptualizing this line that it makes even more sense given the shape of the inputs that we have. And that is a position for a rock. And a position here includes the x, y, and z coordinates. So this is a tuple in Python, if you want to think about it that way. It is equal to the time plus times the initial position plus, times the velocity plus the initial position. So the rock starts somewhere, or the hailstone starts somewhere, and over time it will be traveling somewhere, and then this becomes a function of t, right? So what is my position at a given time? This is sometimes called, I guess, a parametric way of writing a line or something like that. The two are similar in spirit, but they are conceptualized differently, right?
Yeah.
Now, what's interesting about this is that I can think of this line now as like this target that I can move, and I can go at any point in time and ask, where was the rock back then? Or where will the rock be in the future? And it's very convenient to think about it that way because we are given the positions and the velocities. So no transformations needed. Great. Okay, so now I said that the positions and the velocities, and the velocity is not v0, it's just v. The positions and the velocities...
There's no acceleration, so it's not complicated. But I guess you could have acceleration as part of this formula too.
Yes.
Yeah. Okay.
So I said that this is actually P0, V, and P are actually 3 dimensions, right?
Yeah.
So what happens if I break this into 3 dimensions? Then I will be asking questions about these 3 dimensions separately. Oh, my replace did not work well. I'll not bother. Now, for each of the 3 dimensions, you can plot a graph. And the graph will have t on the x-axis and, let's say, px on the y-axis. Naturally, we'll have to do this 3 times for the 3 different axes. Then, let's go to Desmos and plot the examples. Oh no, Desmos doesn't remember our previous inputs like XCollyDraw does. That's too bad.
Maybe you have to log in.
Maybe, but not right now. So remember, the y-axis is one of these 3 axes. It's going to be x, y, or z. So y equals, the x-axis is time. So it is, coming back to the formula here, it is the velocity time plus the position. I guess I will invert this so that it lines up with this representation. So it's the initial position. I'll leave this there. The initial position, which is 19, plus the time, which is the x-axis, times the velocity, which is -2. So I will write it as -2x. Then for the next hailstone, it's this. And for the next hailstone, I'll do 3. That. So remember that this is a graph of where the hailstone will be on the x-axis of that space and over time. So they will start at this x position and they will go down. So we can tell that, for instance, rocks green and red are parallel in the x-axis. And because they're parallel in the x-axis, it means that they are parallel, period. These 2 rocks will not intersect. And you do the same for the y and z coordinates as well. Okay. So next, you have to think about the rock that you are going to throw. And of course, the rock is thrown in 3-dimensional space, but let's pretend for a second that it's only thrown in a 1-dimensional space. We want to hit the trajectories of the hailstones on the x, projected, like drawing a shadow on the x-axis. And we want to hit that. Well, there are different ways of going about this. We can go this way or we can go this way. And given enough slope, we'll always be able to hit all of them. So for instance, I will draw a different color. I guess I have to write the formula first. So my hailstone is going to be y equals, let's put the hailstone all the way up, so like 30. And let's make it go down really fast, like -5x. And then my hailstone is guaranteed to hit all the rocks. So that's one way of doing it. And I'm going to configure this to be a dotted line so we know that it is the rock. Alternatively,
I think your screen has frozen. Sorry to interrupt you. I think it was. Sorry to interrupt you, Leandro. I think your screen is frozen.
How about that? Is it better now? I restarted the screen share.
Oh, okay. Yeah, it just takes a little bit of time to kick in.
But
it's probably.
Do you see me now?
I think there's just some latency, so I can't see anything yet, but I can tell it's loading something.
Without a screen share, how can I explain this to you?
Okay, now I got it. Screen
okay.
share's back.
Great. So there are two ways that we can hit all of them. We can either be above all of them and go down, or we can be below all of them and go up. And these are the two ways that we can throw. With me so far?
Yeah. Yeah.
Okay. Now, let's think about the order in which we are going to hit the rocks or hit the hailstones with our rock. If we do black going top down, we are going to hit first blue, then green, then red. If we do, I guess it's red again, then we're going to hit red and green and blue. And similarly, if we had done this before the intersection here, the order would change, right? Then going below it would not be red, green, and blue, but if we did something like this is too much, this is not enough. Yeah, if we have done something like this, then it would be blue and red and green instead of red, green, and blue, right? So the order depends on whether you are going in this direction or that, and it depends on your time with respect to the intersections. But we know how to compute the intersections. That was part one.
Yeah.
So we know the order that we can hit. We can either do blue, red, green, or red, green, blue, or blue, green, red, but we will never do something like blue and then I don't know, but there are some orders that are impossible. I don't think I can visualize any of them right now.
I think they're all possible with this current.
Yeah, maybe in this configuration they're all possible, but it is the case that if you had a third rock that was parallel,
in between.
So it's always the case that you're going to do either blue, red, and green, or red, green, and blue, but you will never do red, blue, and green, for instance.
Yeah.
So taking in account all the intersections and taking in account all these rules of ordering, you are able to devise a set of constraints. So the set of constraints is going to have information like I can reach blue before red and I can hit red before green in this direction. But it will not have stuff like I can hit going in this direction red before blue, right? So there will be a set of constraints that, and not only about the order, but also about having to do with intersections. So between times 0 and 1, I am able to do blue, red, and green. And between times 1 and infinity, I am able to do, or even 1 and 2, I'm able to do red, blue, and green. And then between times 2 and infinity, I'm able to do red, green, and blue. So there is a set of constraints that has to do with the order and the time intervals.
Yeah.
Now, take this big ball of constraints that you devised for the x-axis, mush it together with the sets of constraints that you found for the y-axis and the z-axis, because you cannot hit the blue line for the x-axis and don't hit it for the y-axis. The hits for the blue line are going to be simultaneous on all three axes, right? So you have to mush these constraints together so that you find one solution that will satisfy all of them at once. So you will end up finding that in the interval between 0 and 2, you can do blue and green. Oh, but in another axis, you could only do blue and green between 0 and 1. So cut out the period between 1 and 2, for instance. And you start chopping the space using the constraints. That's what I mean by mushing the constraints together. In the end, my theory is that you are going to end up with a single place in the Cartesian plane. You will start with like 0 up to infinity, but as you section things using the intersections and the orders and all the constraints and all of this complicated thing that I talked about, I think you will end up with a single point in the space, and that's going to be our answer.
Can you explain again how you carve up the space? I understand that there are some places which are unreachable, but I don't understand how you say, okay, well, it can't be here or it can be there.
Yeah, so let's look at, again, I guess, lines. Let's remove this one and remove even this one. So in this situation, in the x-axis, it is the case that blue comes before green. And you can imagine that the same hailstone, it's the blue hailstone, it will appear in the y-axis graph differently with respect to the green stone or hailstone, right? And in that graph, we could learn that we can only see blue and green between times 0 and 1, for instance. So now we have constrained our search even further. And it will be the case also that in some situations we can say, I can hit blue before green between 0 and 2. And in the other axis, I can hit blue and blue before green between 5 and 7. Okay, there is no solution there. I cannot be before 2 and after 5 at the same time.
I see. So you start to kind of build a graph of dependencies where it's like from this to this.
I wasn't even thinking of the graph, though I suppose you could conceptualize it that way. But I was thinking more of like, I was thinking in the lines of a set solver, like just accumulate constraints and try to find a solution for them by perhaps even doing the transitive closure of the constraints.
Okay. So like linear programming kind of vibe. Hello? Yeah. Okay. So the constraints, if you could spell out the constraints for this particular graph, it would be
the constraints are on the x-axis, blue before green at 0 up to 2, and green before blue at 2 up to infinity.
Assuming
on the x-axis and with a rock going up, or going up is not really a good way of describing this, I guess. Increasing, or rock velocity positive, right?
Yeah.
Positive.
Yeah.
And then
another
another constraint would be like so. And the rock is going negative velocity.
Yeah. That makes sense.
And then the way that we can constrain this is, let's create some more constraints. So on the y-axis, no, the y-axis has an independent velocity, so I should not think about it that way.
I guess in another dimension.
Yeah, no, I think that thinking about the y-axis is maybe the way to go here. But yeah, it is the way to go. Let's continue with this. So I'll just change the 2 into a 1. And then what you're going to do is mush together not the the positives and positives, but positive and the Cartesian product of positive, negative, positive, negative. So you will look at x-axis, y-axis positive, x-axis, y-axis negative.
Why is it 1 for the y-axis?
Here, I'm making this up.
Yeah. Okay, so just arbitrarily, if we were to look at the second column in the input.
Yeah.
And
I'm claiming that if you were to look at this second column in the y-axis here, you would end up with these constraints.
Yeah.
But what we would learn is that if we want a rock that goes this way, then it must be the case, and perhaps we could make this more interesting. Forget about the graph now. I'm going to make up values to make this more interesting. So now this goes from like 1 to 3. And this from 3 to infinity. Just making things up. But and this goes from 0 to 2, for instance. So if I want my blue to appear before the green, then I need to merge together this interval with this interval, which becomes from 1 to 2. Now, of course, there was an intersection here, but if there wasn't, then we would learn, like if we saw that, for instance, this was like from 5 to 7, there would be no intersection between this and that, and then we would learn that if we want to throw a rock in the positive direction in both axes, blue must not come before green. That's impossible. So green must come before blue. And if we are able to prove that blue cannot come before green and green cannot come before blue, then we have proved that the rock will not go in both directions positive. One of the two must be negative. And with that, we can start pruning the search space because, of course, we don't want to do the combinatorial explosion of all the constraints.
And how does this, because right now how does this end up with a point in the end?
Well, we will end up with
right now,
some false paths, but we will end up with something like this. And my claim is that after you mush all the constraints together, you will end up with something like this. And it will be like, aha, I am at this position.
Yeah.
Or this position, no, not actually this time. I am at this time. Remember that this is all about the x-axis, right? We were looking at these intervals here that are in the x-axis. So you're going to say, aha, to hit all the rocks, it must be the case that I have hit the blue rock at time 5. And to have hit blue rock at time 5 and the green rock at time 7, it must be the case that, and then you do some, you solve some equations to find the original point here. But you will find like this point and that point, and from those two you can find this point.
Yeah. It makes sense at a high level. It's a bit hard for me to wrap my head around at the moment. But do you feel like you could implement this?
I started implementing it, and so far so good. I have a notion of...
Okay.
I have a notion of parsing the hailstones. That's easy. I have a notion of finding the intersections, which are the times. So now I'm looking at time versus the x-axis, for instance. And I can find all the intersections using the part 1 solution, nothing fancy here. And then I can look at the orders in which I'm going to see the lines. So I can like trace this red dotted line, and I can tell you, oh, I'm going to see blue, then green. So this is what I implemented. And then it becomes a simple matter of doing interval arithmetic and breadth first search, something like that, in the search space. And we have done some interval arithmetic, so I'm going to borrow that from the previous days. But yeah, it's kind of tricky. The mushing of the constraints together is, it's not a lot of code, but it's detailed code. It's like the code that we wrote for one of the days in which the solution was like 5 hours of drawing, 10 minutes of coding. So it would be something like this.
Okay. Got it.
At least it's not my first time doing it, because this constraint satisfaction problems is something that I worked on in grad school. So I should be able to do it.
I'm sure.
And
yes. Do you want to give it a go?
no, not right now, because I also wanted to explain day 25, because I did a smart solution for day 25.
Okay.
So day 25 was, you have a graph in which this node connects to this tree, and it's not a directed graph. And this node connects to this tree, not a directed graph, and so on. And then we want to find what are the three edges that we can remove such that the graph is going to partition. We are going to completely separate the two graphs. So there are all these roads. What are the roads that if we were to close, then you could not go from any city to any other city in the map? There are three main roads that service the area. What are the three roads? That was the question, right? Remember this one?
What were the roads? Oh, yeah. I remember.
Yeah. And we solved this by plotting the map, looking at it in GraphViz and finding the three roads, and that was our answer.
Yeah, you called this the dominant nodes earlier.
What?
You called these the dominant nodes, like a node you pass through. So what are the dominant nodes? I guess, or the most dominant nodes?
Yeah, and perhaps I could have done that using this, but my idea was, I just implemented an idea that we saw on Reddit, but I thought it was interesting enough to share how I implemented this. So what I did is starting at every possible node. So I'm going to start on this node. And then what I'm going to do is I'm going to find the shortest path from this node to all other nodes.
Yeah.
And while I'm doing that, I am keeping track of which edges have been used in these shortest paths. So if I need to go from here to there, but I pass through this, then I'm going to count the edge between this and that once. And I do that over and over for all possible inputs. And then I look, what are the three most used edges? These must be the edges that connect the two different parts of the graph. And that's your answer. That's how you do it. Remove these three edges, and that's your answer.
Yeah, I remember this solution too. It's a really nice solution. I do think, though, that it seems like so that's like an n-squared solution, right? Because for every node, you have to traverse all the other nodes.
Yeah.
You have to traverse potentially all the edges. So it just feels like you should be able to do this in a single pass.
Yeah, because if you have computed the shortest path between this and that, and then between this and that, if you're asking now the question about between this and that, you should be able to combine the two previous answers, right? Dynamic programming.
But that's true. Yeah, that's true.
So you could have done that. I didn't. I just brute forced it, like I explained, and it is like a minute of runtime, something like that. And there was another optimization that people did on Reddit, which I think is interesting, which is just like, don't do it for all of them. The pattern will emerge soon enough. Pick a bunch of them randomly, run it like a certain number of times, and that's your answer. You don't have to do it for all.
Oh, yeah. You'll start to see like a few are emerging as the winners.
Yeah.
Yeah.
So yeah, I thought that was kind of a neat thing. So I have here the smart solution. This is what it looks like. First, we do the part of counting. We are counting the uses of edges. So every time I use an edge to go somewhere, I count it. And I do the sorting so that I only find shortest paths, as we have done in the past several times. And then that's the full algorithm. The rest that you see here is to actually answer, because they always have to ask us a number, right? And the number that they wanted us to answer was like, what is the size of the two partition graphs multiplied? So this is me doing some breadth first search to find all the nodes in one of the subgraphs. And this is me removing edges.
That makes a lot of sense.
Yeah. So there is not a lot of interesting, juicy bits here.
I like that, though.
It works.
Now I know, next time I have that problem, how to do it.
Yeah. So the only thing left for us to do is to think about day 24. And I think what I'm going to do is try and flesh out this whole constraint satisfaction implementation that I'm thinking about. But I would love to hear more ideas, because you tend to come up with some very smart ways of solving things.
Yeah, it's not really coming to me yet, but this does seem very complicated.
I'll leave you to it. And then next time we can either share the full solution because we solved the problem, or we can work things out together.
That makes a lot of sense. I'd like that a lot.
Yeah, and I'm actually looking forward to seeing how people solve this. I want to see if there's like, oh, this is just an application of blah, blah, blah theorem. Or if it will be like a matter of a simple for loop.
Probably. It would just be a for loop.
I do want to say hello to Bo.
Happy New Year, Bo.
And Sam is here and say, I'm not a code guy. I didn't know why YouTube suggested me this video, but I came here to support because I saw when people were watching. Yeah, that's what happens when we don't schedule streams in advance. We just show up. So it goes. And Shub is here. Hello. And with that, we'll sign off. And next time, we'll work more on day 24. How about that?
That sounds great, Leandro.
Yeah.
Good to see you, and Happy New Year again.
Happy New Year. Nice seeing you. And thanks for coming up with the crazy idea of doing Advent of Code. It's ruining my night. Just one night that I spent on this, but it ruined that night.
It's been a ride. It's been a ride. We're almost there.
Yeah, it ruined a night in a perfect way, because it was a very pleasing night. All right. Bye. See you soon.
Speak soon. Bye.
Thank you for watching the stream, you know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.